Your next homework assignment is 3 questions instead of 2, so that means you should give yourself 1.5 times as much minutes to solve. Actually, I don't think that's true. I think that these problems are probably easier than the last couple of assignments. By the way, on the assignment that you submitted today, if you have any suggestions on how I can give hints to students but not give too much away, I'd definitely be interested in that. I'd be interested in your feedback on how can I guide students in the right direction on this problem without giving away the farm, you know? I'm thinking about putting at the top of the assignment, start this immediately. Start this assignment immediately. Like, skip the rest of your classes for the day and start this assignment. Because then if you wait until Monday night, then nobody's around to, you know, help you pick up the pieces when it goes weird. So if you have suggestions, really tell me, because I'm always trying to find ways to explain this, the nodal method a little bit better. This problem's a tricky one. So anyways, your next assignment hopefully won't be that ugly, but it's always a good idea to skip the rest of your classes and start on your hydraulics assignment as soon as you get it, right? Okay. Well, we're going to continue with Excel today. And before we get to example 2, which is, I've got a handout for you, and this slide pertains to that, I thought that what we'd do is take a look at what we were doing on the board last time. Because we were going through the process of making our columns and doing the calculations just so that you would see what the structure of a Hardy cross problem looks like, you know, like why we're doing certain things. So you can follow along with this one if you want to, but it may be just as well for you to just watch what I'm doing on this one, and then there's another example that I'm going to have everyone work on, and I'll circulate around and help you troubleshoot that example. So it's your choice on this one. What I'm going to be solving is the 2-loop problem where you've got 100 units of flow going in and 100 units of flow going out. We've got fixed R values for this one. So on this one, you're not actually even calculating F's or updating the F's. And so this is a little bit simplified compared to the example problem that you're going to be tackling in a minute. But for this first one, our column headers are iteration, loop, pipe, N value, R value, Q, R times Q times the absolute value of Q, and then N, R, absolute value of Q, delta Q, and then finally corrected Q. All right, so what you'll remember is that, you know, the success of this whole operation depends on us getting a correct first guess. And I don't mean correct in terms of it has to be evenly balanced one way or another. I mean at each junction the continuity has to be satisfied. So I could do 1 here and 99 there, and it'll still, you know, as long as at every junction continuity is satisfied, it'll still work out. That's one of the important musts of this process. So I'll start with iteration 1, loop 1, and the pipes are 1, 4. I think that means January. Okay, so 1, 4, pipe 1, 3, pipe 3, 4. And then when I get into loop 2, I'm going to have pipes 1, 2, pipes 2, 3, and pipes 1, 3. All right. The N value for all these is 2. How come? What does that mean? 2. Why 2? Anybody remember what 2 means? It means I'm going to be using Darcy-Weisbach's equation for friction loss. If you're using the Hazen-Williams, then N would be 1.85. So I'm going to be using Darcy-Weisbach, and that's why N equals 2. Okay, the R values are 6, 3, and 5 here, 1, 2, and 3. So this is just exactly what you had on your paper from last time we met. Okay? I'm going to put in my initial guess flow rates of 50, 15, and negative 50. Where does the negative come from? Why is it negative 50 for pipe 3, 4? It's direction, right. So here is pipe 3, 4, and I said clockwise is positive, and this flow is against the clockwise direction. So I'm saying negative 50 there because that has to do with the direction. All right. All right, so here we start with the equations. We've got equals R times Q times absolute value of Q, F2. Since I've got it centering it, the equation starts bleeding over to the other cells, and so I can't click in the cell like I ought to. Let me turn off that center justifying until I've got it set up. Okay, so this one I can just drag down because it is R times Q times the absolute value of Q. Okay, and 15,000, that's what we had when we were doing this on the board, so we're on the right track so far. Drag that down. You'll notice that here we've still got a negative result when we had a negative flow rate, so that means our absolute value function is working the way it should, because one of the Q's is in the absolute value, the other one isn't, and so it retains positive or negative sign, whichever. Okay, so here is N times R times absolute value of Q. Yes. Drag that down. All right. Now, if you remember back to the formula, what we're all doing this for is this magical formula here. Let me copy it and paste it over here. So this formula, it's not really magical. It allows us to ensure that if we do it enough times, we're going to have a balance in the flow rate and energy loss, so that regardless of which route the flow goes in the pipeline, that you're going to have equal head loss in any of the routes. And that's something that we know has to be honored, that you couldn't have two different paths to the same point and lose different amounts of energy. That wouldn't make any physical sense. And so the process of iteration using this equation is going to do that. And so it says that we have to have the sum of R times Q times absolute value of Q, so equals the sum of these things here, enter, because we're going to use that in the numerator of our equation. And down here we want the sum of these ones. Okay, I'm going to put that in italics just to make sure that we know that this is like something special. It's not the calculated rows like it was for the pipes. It being in italics helps us remember it's the sum of the cells above it. Now you're going to see me do something you're not going to believe it. I'm going to type in the equation 3 separate times. Rather than like dragging it down or anchoring it, it's better to type it in 3 different times, because when I copy and paste my iteration over and over again, I want it to be a relative reference all those times. And so this equation is equals negative, because here's our negative sign, this divided by that. And now I'm going to do the same exact thing. Equals negative this divided by that. Equals negative that divided by that. All right? Trust me, it's better to type it in 3 times than it is to try and anchor the cell references. Now corrected Q is the original flow rate plus this correction, the delta Q. Okay, so now we've got our updated flow rates. All right, so now let's put in the flow rates for the second loop. Pipe 1, 2 is 15. Pipe 2, 3, negative 35. All right, what do I do now? I'm in the danger zone. What is it? Negative 12, right. Instead of typing in negative 12, I'm going to do equals negative and refer to that location. Because the relative reference I can copy and paste in a way that makes iteration very simple. All right. So right there, that's one of like the favorite mistakes. Like it's on the top 10 list of mistakes.
They are testing the fire alarm system, so it may go off.
All right.
They'll often get you if it's acting on fire.
All right. Don't. We'd rather burn.
Or I won't come get you if I want to get rid of you.
Yeah, right. We'd rather burn than miss this example. All right. All right. Okay, so now I just do the same thing. Actually, I can copy this. See how I'm highlighting? Copy. I go down here, paste, and it just does the calculations for me because it's just, you know, multiply this, then that, then the absolute value of that. I can do the same thing over here. Copy. And down here, paste. It's not pasting the numbers from above. What it's pasting is the formulas. Okay? And I could do the same thing here. Copy, which is Control-C. Control-V is paste. And it does the summing calculations that I need. All right? Now, the delta Q equals negative that divided by that equals negative this divided by that. All right. Seems like they could test the fire alarm after hours, doesn't it? That just occurred to me that maybe they're not being so focused about when they test their equipment. All right, so the corrected Q is this original flow rate plus the delta Q. And we drag that down. All right, so everything's looking good on the first iteration. Any questions? It's totally okay if you're just watching this one rather than trying to solve it on your own, because you'll get the practice when we do the example in a minute. All right, so now what I do is I am going to, I'm debating in my mind whether I want to copy everything or if I just want to copy the things that don't change. I'm going to copy everything. So just highlight everything. Control-C is copy. And I'm going to paste it down here. Control-V. So first thing I need to do is it's iteration 2. All right. Loop 1, loop 2. That doesn't need to be changed. The label numbers, those are constant. The N values are constant. Now in this example, the R values are constant. But if I was using F values, then I'd have to calculate an updated F value based on the flow rates from the previous iteration. So we'll get to that. Now, I need to modify these flow rates because none of these are correct anymore. I don't want to have my initial guess of 50 because I can do better than that. The better flow rate guess is equals, and I'll just click up here where I have the most updated flow information for pipe 1-4, right there. So everything else automatically adjusts. Where's my best flow rate guess of pipe 1-3? Right up here, huh? No, no. Equals negative of this one. Why the negative sign? It's that our perspective has changed. Previously, we were talking about, you know, from 1 to 3, when you're in the perspective of loop 2, that's a negative flow. But then when you're looking at the same pipe and the same absolute flow direction, when you're in the perspective of loop 1, then that's a positive flow rate. So it's not that the flow rate actually changed direction, it's just that our perspective changed because we're working in loop 1 now and we're referencing a value from loop 2. So that's why it's equals negative of that amount. And then 3-4 equals that. All right. So here's some encouraging signs. Our delta Q is getting smaller. If you don't see that, then that means the solution isn't converging like it needs to. All right, let's update this. Pipe 1, 2, our best flow rate equals this. Pipe 2, 3 equals that one. And pipe 1, 3, it's already doing what it needs to do, because in loop 2 of iteration 1, we were looking up at the previously calculated value of the flow rate. So equals negative of the most recent flow rate. All right, so it also has a smaller delta Q. The delta Q is getting smaller. So now it really gets easy. Copy, paste. You have to maintain correct spacing or else the relative references will mess up, as you saw in a previous example I did in Excel. So paste, and let's just change this to a 3 and then make sure that our references look okay, like it's looking where it needs to look for the flow rates. Yeah. And these delta Q's are getting nice and small. Let me do view, split. Oh, I don't need to split it like that, though. So what I can do if it's split is I can keep my column headings and see them while I'm scrolling down here. Okay, so look at the delta Q. Our first delta Q was 2, and then 0.3. Now it's 0.01. So it's getting nice and small. And the flow rates aren't changing much now either. Here's 47.7. Here's 47.7. Some of them are still flopping around a little bit. 1.7, 1.3, 1.3, 1.5. So we need to find the middle ground on pipe 1, 3. So let's do another iteration. Control C, Control V, and all I have to change is this one cell, the iteration number, and really no calculations are based on that. But now you can see that this delta Q is just minuscule, and we finally have a flow rate. Pipe 1, 3 was the last one to stabilize, and now we know the flow rate is 1.5. 1.512 is the flow rate in that pipe. So we're done. These are the correct flow rates. Any questions about that? All right, well, let me give you the example. The example bumps it up to the next level, because in the end, when you find the flow rates, I'm going to ask you to calculate pressures. And the way I do that is I say the pressure here in one of the locations is known, and then all you have to do is just calculate the head loss based on the R value and the flow rate, so that the pressure is either increasing or decreasing according to the flow direction. Oh, that wasn't so bad. All right. On one side is the question, on the other side is the solution. Well, at least it's a view of the last iteration, so that as you go through your calculations, you'll know if you're getting close to the right answer. Yeah, that's right. You could have as many loops as there are. Now, in this one that I've just given you, you have to start off with your pencil. You don't jump right into Excel. What you're going to have to do with your pencil is find some flow rate, like do the continuity equation. You have to find out, and not everybody has to do the same thing. And you'll notice that on your paper, you can't see where I started because you've just got the last iteration. And so it's not obvious what my initial flow rates were. Here, I'll take those. Need one more? There you go. All right, so we got practice with that last time, this initial flow estimation thing. You can collaborate with whoever's sitting next to you if you find that useful, but split up the flow rates, write them on the paper, and take a look at the columns that I've put, flip over to the back side and look at the columns, because it's a little bit different than the columns from this one. Because in this example, now I'm asking you to go all the way and calculate an updated F value. And then to help you see when the solution is converging, I've added this percent change column. So But the first step really is just to do yourself a flow balance and then have someone check to make sure it looks right. And then you can start typing in those column headers in Excel. We've got 4 minutes remaining, so I'm just going to go through the highlights of this solution, show you the common pitfalls, like where do people usually make their mistakes. And you've got the solution here, and I'm happy to continue to help you make your spreadsheet. You can come see me and we'll keep going over it. But okay, so here's the common mistakes on this. So we start off our F values with just fully turbulent flow assumptions. Don't forget to switch back to the full Jane equation in the second iteration. So you see now I've got the full Jane equation for my F values once I have the Reynolds numbers from the previous step. The other common mistake that students could potentially make is, where are our common pipes on this one? It's CE and EF. So CE and EF, those I always need to go look for the flow rate that's the latest and greatest flow rate. So here you can see I don't have my initial guess flow rate for those two. I'm doing the negative of the corrected Q from the previous step. Now, why am I bothering with these columns of absolute value, absolute velocity, Reynolds number? These two columns are really just to make it easier to solve the Jane equation in the next step. Because if you look at my Jane equation over here, I'm referencing the Reynolds number from the previous iteration. That's why I went to the trouble of calculating Reynolds number over here. It was just as a tool for my next step. And then, of course, the percent change, that's not a part of the solution. It's not to actually be used in the calculations. It's just so I can see how close am I getting to convergence. And so I can see that by the fourth iteration, most of the pipes are down to 1% convergence. And so I declared that good enough. Now these pressures, if you're given a pressure at A is 600 kilopascals, I calculate the head just based on that pressure divided by the unit weight of water, which is 9.81 kilonewtons per cubic meter. So what's the head and the pressure at pipe B? Okay, so the water is flowing from A towards B. So the head at B is going to be however much head there was at A minus the losses. So you can see I've got the initial head at A minus the losses. And over here in my last step, I'm calculating the pipe head loss. So the head loss is going to be, I'm using the Darcy-Weisbach equation, FLV squared, FLQ squared divided by D2GA squared. So that's where this is the head loss through the pipe, just using the Jane equation in terms of Q. And so the head is going to be the head upstream minus the losses. C, the head at C is going to be the head at B plus some pressure. So now you can see that's a plus because of the flow direction. So the common mistakes are going to be people who forget to swap the sign, like in the common pipe, CE. So don't forget to, when you're doing the flow rate, add that negative sign there. And then the other common mistake is when you're calculating the corrected Q, the delta Q, to have the negative sign in that as well. All right, I regret that we don't have more time for this. Work on it, get it all sorted out, and then we'll spend just a couple more minutes in class is today Tuesday? On Thursday, we're going to, we'll revisit this on Thursday, but I would like you to solve it between now and then. Rather than starting on the homework, I think you should solve this spreadsheet to have like in the background as a resource and a tool and a reference for yourself so that you can solve the homework when it comes up. So that's it for today. I will see you on Thursday. Finish the example if you can. If you need help, stop by and see me.